All right, so sorry for the delay, you guys. I forgot my computer back in my office. Happens to everybody every once in a while. So obviously we're not having the exam today. And again, some of you won't be happy about it, and I understand that. You've been studying, getting ready for it. It was just a matter of there was enough students, about 10 out of 80, that had legitimate reasons why they couldn't make it. And instead of doing a one-off kind of makeup exam for them, I just pushed it back for everybody. So I know a lot of you have physics today as well too. So maybe that helps out, but it was a tough decision to make, but I thought overall it was kind of the fairest way to go about it. So as a kind of makeup gesture, like I said, I have the exam that I was going to give to you today. I'll post solutions for that as well too. Obviously it's not going to be the same exam that we're going to have next Tuesday, but you'll get an idea of scope, difficulty, stuff like that. So any questions about how things are getting rearranged? Midterm on Tuesday, covering the same scope of material. Yeah, question?
Will the homework be postponed?
Yeah, we'll postpone the homework probably until the following Monday or Tuesday. Yeah, so, I'm working on posting the 2 extra credit assignments related to one of the lectures that actually 2 of the lectures that we're skipping over right now that I'll talk about briefly, but you'll also have those in the interim to work on as well too. Okay, so what were we talking about on Tuesday? I know a lot of you are thinking exam, but we did cover new material on Tuesday that is not going to be on the exam. What were we talking about?
I think we had just moved on to beams 3.
Yeah, beams 3 and beams 1 and 2, refresh my memory. Beams 1 was review because it was all what?
Shear moment.
Yeah, shear moment diagrams. So how's everybody feeling? Are you feeling better about shear moment diagrams? It wasn't until like my junior year of my undergrad that I really started to get that kind of intuitively. So that's why we cover it like 3 different times. So statics, strengths, you'll see it again with respect to frames. So like not just straight elements, but like kinked elements in your junior level structural analysis classes. So it takes a while to get used to that. And that's why we really hit it hard multiple times throughout the curriculum. Beams 2 was what? What do we do with V or M once we got it from the beam diagrams? Yeah, bending stress. And so we basically had M times some distance divided by I, whether it's MZ times Y over IZ, or MY times some Z coordinate divided by IY. And so that's biaxial bending. We could have 2 different moments to deal with. We walked through the rest of that example problem. I put a video up online for that as well too. And then the other wrinkle that we can put into the bending stresses would be 2 different materials. And we talked about transforming the cross section into all one material to have the same effective stiffness. And that's what I want you to be comfortable with. That would be fair game on the exam. I'm not going to make you go through all the stress calculations, but if you can take a cross section, made out of 2 different materials and transform it into a single material by changing the width, that's what I want you to be able to do. Okay, so then beams 3, what were we starting to do in beams 3? Shear. So V and M diagrams, we dealt with the M, now we're dealing with the V. And so that's what we started with this kind of long example right here, where we've got a cross section subjected to just some internal shear. Now, do you think that there's many beams that only have a shear acting on it? Can you think of any kind of a beam where you'd have, like at every location, just V and no M? What do you think?
Yeah,
Horizontal and pin connected. So like pinned. So something like this. Is that what you're thinking, Dylan? And then what kind of a load would we apply to it? Only a vertical load, so maybe a load like that. I'm still going to get shear, so my shear diagram is going to look like this. Am I going to get a moment as well? Yeah, my moment diagram is going to look like this. There might be a couple instances where we have, based off the loading, maybe a region of a beam with 0 shear, but we'll never have the entire beam have zero shear, but we could have regions of zero shear. We could have regions of zero moment, but for a beam subject to any kind of actual loading, there's always going to be some moment, there's always going to be some shear. Now there is one, there's not really any exceptions to that. We could think of some sections of beams that might have zero shear or zero moment, but somewhere on the beam, we're always going to have shear. Somewhere on the beam, we're always going to have moment. So why are we just looking at the shear here? Why do you think all that I care about is looking at the shear?
Shear stress.
Yeah, shear stress, I mean, but what if I had a bending moment on here as well too? Why am I not considering that right now? Oh yeah, so Musad's saying maybe because the I shape's really good at resisting the bending moment. How about just for breaking down things into bite-sized chunks? I mean, that's really all that we're doing. And the conceptual kind of issues that I've been talking to some students about is they said, you know, when do I know to do this kind of analysis, like a shear stress due to a shear force analysis versus like calculating the bending stresses due to a moment? They say, I see these problems that only have a shear force on them. I see these problems that only have a bending moment on them. And so what do you think the answer is? What if I had a beam like this that had a shear force and a bending moment applied to it? Do we know how to deal with that?
Yeah.
How do we deal with it? Break it up into bite-sized pieces and add up the results at the end. And so when we look at our formula sheet, we have this table right here. And basically, at this point, you know, we're not quite all the way through the example for shear force, but we've done normal force, torsional moment, most of shear force, most of bending moment as well too. We're going to skip over thin-walled pressure vessels. That's going to be extra credit because it's really super simple, and you can pick it up as you need to down the road, but I will provide extra credit for it. But is it possible that we could have a cross-section that has all of these loadings on it at the same time?
Yeah.
Absolutely. Now, the only shape of a cross-section that we could actually apply all of these equations to or deal with all of these equations with, what shape would that cross-section be? What do you think? We can only deal with circles because why? You're exactly right. Yeah, torsion, we were limited to only circles. So if I were to give you a problem with what we call combined loading that has a cross-section and it has a normal force, a torsional moment, a shear force, and a bending moment, if it's a circle, you have all the tools to figure it out. Yeah, Max.
Is that because, well, I mean, obviously you could put a bending moment on a beam, but like, is that just because we wouldn't do that generally?
Just because we don't have the tools in this class to deal with a non-circular torsional shaft. So it's absolutely correct that a torsional shaft could be rectangular in cross-section. We just don't get to that level of analysis in this class. There's a non-linear stress distribution when it comes to rectangular shafts or non-circular shafts subject to a torque. So our toolbox from this class only allows us to deal with a circular cross-section. Now, could I deal with a circular cross-section if I have a normal force? Yeah, area is just pi r squared, right? I can deal with a circular area, not a big deal. Can I deal with a circular cross-section for a bending moment? We haven't already, but what do I need? What kind of geometric properties do I need when I'm calculating the stresses due to a bending moment?
Radius inertia.
So I need a moment of inertia. Can I calculate the moment of inertia of a circle? We haven't in this class so far, but on this note sheet, we absolutely have information about the moment of inertia for a circle. We have the equations. Just like we have it for a trapezoid, a triangle, stuff like that. So I could calculate I for a circular cross-section. And what's the other bit of geometry that we care about when we're calculating bending stresses? It's m times what over I? Yeah, y. So whatever my point of interest is, I just need to be able to calculate, well, what is the distance, you know, in the y direction? What's the y coordinate of that point? And we can do that with a circle. I mean, either it's given to us or the angle and the radius is given to us, but we can calculate the coordinate of a point on our circle. Like, that's not a big deal. So we can do moments, the bending stress is due to a moment on a circular cross-section. There's nothing keeping us from doing that. And I think that one of the recommended problems for this next chapter is going to give you a circular cross-section that you'll have to deal with. So you have all the tools to do that. Just the fact that we've been doing mostly rectangular parts of cross sections doesn't mean that you don't have the tools to be able to do it for a circle. All right, the trickier one's going to be shear stress. So shear stress due to a shear force, what's my equation for that? Let's go ahead and refresh our memory. Tau due to a shear force equals what? VQ? Right, the shear force times the first moment of area for our point of interest, and we'll refresh our memory about that because we talked about it on Tuesday. The moment of inertia, we just talked about that. We know how to do that for a circle, and T. Now, Q and T get to be a little bit tricky when we're talking about points that aren't on like the diameter or aren't the top or the bottom of the cross section. Now, so for like a long homework problem, or like a homework problem where I give you, you know, it's not something that's going to be on the exam, I could potentially give you something like that, because if we're looking at, let's just talk about that generally. If we're looking at a circle like this, let's look at 3 different points of interest and figure out how we would deal with it. So here's my neutral axis for all of them. Assume that shear is going vertically downwards. If my point of interest is the top, and I'll just put the shear force on here just to make it really clear. We're talking about shear force like this, like this, like this, all right? If my point of interest is on the top, again, we know what V is, we can calculate I, we already talked about that. What is Q going to be at the top?
0.
It's 0. Why is it 0?
Because if I check the above area is 0.
Yeah, so if I were to make like a cut or draw a line perpendicular to the shear, I'm going to get an area on top and an area on bottom, because remember, Q is simply equal to y bar prime times a prime. This line separates like a prime up above or the option of a prime down below. If I choose all of the area above this point of interest, a prime is 0, right? Y bar prime would be some big number, but the area above that is 0. So that means 0 times some big number is just 0. If I chose everything below this line, A prime is going to be the entire area, right? So why isn't that going to be 0 for Q? Yeah, what is y bar prime? How would you describe y bar prime to somebody who's been in this class up until right before last lecture? It's the distance from the centroid of the entire shape to the centroid of A prime. The distance from the neutral axis of the cross section to the centroid of A prime. And inevitably, students are going to say, well, isn't this y bar prime for this like area down here, if I choose the area down below? And it's not, because it's the centroid of A prime, which would be right there. And the distance from here to the neutral axis is 0. And that's why it doesn't matter whether we choose A prime above the point of interest or below the point of interest. We get the same exact value for Q. And in this case, Q is going to be 0 because either A prime is 0 or y bar prime equals 0, depending on which side you choose. Okay, so here, clearly Q is going to be 0. So what's the shear stress at the top or the bottom of the cross section always going to be? 0. Now, some people will say, well, Evan, T is 0 at the top and at the bottom as well, too. Is that correct? It's correct. So why am I not getting like a 0 divided by 0, like undefined type value here? It's because Q is getting to 0 like faster than T is getting to 0. If you did like a L'Hopital's rule, if you took like the derivative of the top and the bottom and you took the ratio of those, you would get a it wouldn't be undefined. It would be 0 divided by like a constant value. So I agree that T is getting smaller up here as well too, but Q is getting smaller faster. So using that general idea from L'Hopital's rule, this would not be an undefined value, it would just be 0 up at the top. Okay, what's the other, question?
We picked a point that has a non-zero Q.
Mm-hmm.
How do we measure the thickness?
Yeah, so we'll talk about that in just a second. That'll be the third scenario. So Musad's saying, what if we would pick like a point like right here, where T isn't 0, how do we deal with Q up above? And we'll talk about that in just a second. But the other kind of easy, relatively easy one to deal with would be at the neutral axis itself. So if my point of interest was on the neutral axis, so it could be there, it could be here, it doesn't matter, any of these being my point of interest, what is A prime going to look like?
Semicircle.
Yeah, it's just going to be exactly a semicircle, either the top half of the circle or the bottom half. So it's going to look like this, and my centroid for that is going to be here. This is going to be y bar prime, and then this is going to be A prime. Now, I can't remember if I give you that equation in the packet or not. Let's see if we can take a look real quick. Yeah, so you don't get a half circle, so I would have to give you that information on an exam, like what is the area of a half circle? That's the easier part. And then what is the distance from the neutral axis to the centroid of that semicircle? I don't provide that to you on the note sheet, so I would give that to you as part of an exam problem. But if I gave you that formula for the distance of the centroid of a semicircle and the area of a semicircle, most of you would know the area, but I'd give it to you anyway. If you knew that, then calculating Q for this would be relatively easy, right? It would be the distance from here to the centroid, I'd give you the formula, times this semicircular area, right? Same idea. So it would be fair game on an exam. I think one of the recommended problems has you doing that as well too, but I would have to give you the equations for both the distance of the centroid and the area of the semicircle. Now, but then what Musa was saying is, well, what if we have like a relatively easy point of interest to deal with? So like this right here, if this was my point of interest, like scenario number 3, that's where it gets to be a lot trickier. So that would be, here's a line perpendicular to V. Here, if I choose everything up above, this would be my A prime area, and we would have a centroid and then some y bar prime value. This is a little bit trickier. It's the same thing where we can get a table or like a diagram that would tell us for, you know, maybe it's defined by the angle of this point relative to the horizontal. Maybe you're just given a vertical distance. There are tools that, and if I give it to you on a homework assignment, there are tools to be able to figure out what this area is and what that centroidal distance is. And I would provide those to you. That wouldn't be something I give you on an exam. That would be something we'd reserve for, you know, like a homework problem or something like that. But this, obviously, no calculations required. I would expect you to know this on an exam. This, if I gave you the equations for the area and the location of the centroid, would be fair game for an exam, and you will see it on a recommended problem. This one, not so much. I wouldn't expect you to do that on an exam, even though I would expect that many of you would be able to figure it out. Yeah, Max?
Wouldn't it be easier to just define a function that would allow you to move the point of interest to any y distance?
And so that's what the formula that I would give you basically does. It just says, you know, if y is, you know, a given value, like distance to the point of interest, what is y bar prime, what is the area? It's basically already a function defined that way. It just depends on whether you're plugging in the distance to the point of interest or like the radius and the angle to the point of interest. There's multiple ways to define it, but that's basically what I would give you, is a formula that would give you y bar prime, a formula that would give you A prime. But again, a little bit more in depth. We're more interested in kind of the first principles and not getting into the relatively more complex geometry, but you definitely have the tools to do it, but for an exam I wouldn't be evaluating you on that so much. But scenario 1, scenario 2, absolutely fair game. So that means that for a circular cross section, it is a great like tool to use to say, let's throw all of the loading at you, N, V, T, M, and see what the overall stress picture is at like a given point. And that's what chapter 8.2 is all about, which is going to be kind of the subject of the lecture today. We're going to wrap up shear a little bit, but then we'll talk about, well, what is like the total picture of stress at a given point, and are all of your stresses due to N, T, M, and V, are they all going to add to each other? Let's get to our table really quick. If I had a circular cross section and it had internal normal force, internal torsional moment, internal shear force, internal bending moment, do all of those stresses add up? Do you just add the values all together? What do you think? Yeah, so the fundamental nature of shear stress and normal stress is completely different, right? One is trying to cause, like a shear stress is trying to cause right angles to change their angles, right? It's changing the angle of each of these corners of a differential element, whereas a normal stress is trying to change like the volume of that element. They're doing fundamentally different things. So right off the bat, I know that shear stresses and normal stresses are going to be kept separate in terms of how they act on that differential element. We'll see how they kind of flow into each other a little bit later on, but for this material, shear stress is shear stress, normal stress is normal stress. They don't really intermingle at all. So right off the bat, I know that the stresses that I get from my normal forces are not going to be added to or subtracted from the stresses that I get from my shear stress due to a torsional moment. But what about the stresses due to a normal force and the stresses due to a bending moment? Are those going to interact with each other? What do you think? If I was looking at a cross section and I was going to cut a beam, here's like my section cut right there. Let's pretend that this has a bending moment applied to it and it has a normal force applied to it. We didn't quite get to this last time. We will get to it in more detail right now, but so bending moment and a normal force. If I were to plot out the stresses due to the normal force, what does it look like? How does the normal stress due to a normal force vary from the top to the bottom of this cross section? Yeah. Due to the normal force? Right, so due to the bending moment, you're exactly right. So if we were to plot out the normal stress due to the bending moment, here it's going to be compression at the top, linearly varying, passing through zero at the neutral axis. So I'll have negative on the left, and I'll have positive on the right. So this is exactly right. The distribution for normal stresses due to a bending moment vary linearly. And that's what we've been going through in chapter, I guess it's 6. Right, this kind of stuff is on the exam. What about the normal stress due to just the normal force by itself? How about this? What is this equation? Equals N over A. Does it matter where I am on the cross section, the top, the middle, the bottom? There's no location-specific property that we care about. Whereas here, it's my over I, so y changes. Here, n over a, nothing changes. So it's the same, and here it's a positive normal force, so I get a positive normal stress the whole way. Yeah, I mean, so what would I do with these? I have the distribution due to the normal force. I have the distribution due to the moment. They're both normal stresses. You know, here's the top, here's the top. They're both acting at the same location. So what do I do with them? Add them together. Superimpose them. We're dividing and conquering, and we're just adding everything together at the end. So if I add these together, what does my stress look like due to the normal force plus the bending moment? What's going to happen at the top? Yeah, I mean, I have a positive number here, I have a negative number here. They counteract each other to some extent. Let's just put some numbers on here. So I'll just say 10 here, and I'll say, so positive 10 here, I'll say negative 6 here, and I'll say positive 6 down at the bottom. So positive 10 due to the normal force, negative 6 due to the bending moment. It's still going to be positive, but it's just going to be a net of 4 at the top. All right, so what about at the bottom? I get, positive 10 plus positive 6, I get positive 16. I just add the results together. This is just like what we did with bending moments where we had a mz and a my. You could look at them completely separately. Just treat like one like a standalone single axis bending moment, and then add it to the results from the other like my moment, just treating it like just one moment acting at a time. Then we just add the results at the end. So that's what we're going to do with normal stresses is, just figure out, well, at the extreme locations, what are the values due to normal force, due to bending moment, just add them together. And so this is one possible distribution that we could get. And so in this case, like the effective neutral axis isn't even on the member itself. It would be like up here where it would actually pass through 0. And so we get some interesting behavior with that, but it could, potentially look something like this as well too, where like we've moved the effective neutral axis up as well. And this happens all the time. So these columns here, they're primarily axial members, but they get bending moment when there's an earthquake, when there's a big wind gust, stuff like that. These are acting as what we call beam columns. And so some of it's going to be stress due to the normal force, like the weight of the building. Some of it's going to be the moment due to like a lateral force being applied to it. All right, so far so good. Does this conceptually make sense? They're both causing normal stresses, so we just superimpose the results. So for normal stresses, that's relatively easy to deal with, but I want to segue to shear stresses now because that's going to help us kind of get back to wrapping up the shear problem that we were working on last time. So if I was dealing with a circular cross-section like this, so we're talking about shear stress now. If I was dealing with a circular cross-section with a shear applied to it and a torsional moment applied to it, let me just go ahead and draw some axes on here just really quick. And I'm going to label a couple different points. I'm going to have point A, B, C, and D. All right, if I wanted to look at the shear stress due to both of these internal loadings combined, I need to do the same thing, is wherever they both act at the same location, add them together. But there's a wrinkle with this because the directionality of the shear stress is basically for a shear force is going to be parallel to the shear force. So at A, B, C, and D, the shear stress just due to the shear force is going to be going in what direction? What direction is V going? Downwards. So let's just break this up. Let's just say this is equal to just the effects of the shear force plus just the effects of the torsional moment. So here's the shear force V, here's the torsional moment T, and if I was looking at those same points, let's just zoom in a little bit. At point A, I'm just going to show the section facing side of that differential element. This is a 3D element, but we're only looking at the front face. And we'll do the same thing at point B. We'll show an exaggerated one at each of these kind of cardinal points right here. And the shear stress is going to be going downwards at every location. Now, I've only drawn it at like this point here at A and at C. And why have I done that? What's my shear stress going to be up here? 0, right? VQ over IT, Q equals 0 up at the top. So, I mean, if I was looking at a point intermediate, let's just add an extra point. We'll call it like point E if we want to. This is going to have, some shear stress applied to it as well. But that shear stress at point E is going to be less than the shear stress at A or C. Let me say that one more time. Because tau equals VQ over IT, the shear stress due to this shear force at B and at D have to be 0. That's where Q equals 0. We already talked about that. At A and at C, we'll get the largest shear stress due to the shear force. We talked about that on Tuesday. Even though T is the largest of the neutral axis, Q gets larger faster, and that's why we get the maximum shear stress at the neutral axis. If I were to go up, not all the way to B, but some intermediate location, I would get still some shear stress at this intermediate point E, but it's just decreasing in magnitude the further I get away from the neutral axis. So big picture, the most important thing here would be the direction of all of these shear stresses. The shear stress due to a shear force is always parallel and in the same direction as V. Is that going to be the same case for T? What is my equation for the shear stress due to a torsional moment? It's been a while, but it's relevant for the exam on Tuesday as well. Equals T, I'll give you that, times something divided by something. T times, yeah, we call it rho. You can call it C if we're talking about the extreme fiber, like the outer radius, and then divided by what? J, exactly right. The polar moment of inertia. All right, but these equations, just like over here, don't tell us exactly what direction those shear stresses are going to be going. This equation tells me that the further away I am from the neutral axis, the larger the magnitude is going to be. So that's helpful. But, so I'm going to look at those same points. I'm going to look at A, I'm going to look at B, C, and D. And we'll even do this intermediate location as well, too. That's a little bit trickier to deal with. I'm going to draw it so that it's, well, let's not even worry about it quite yet. Let's just talk about A, B, C, and D. Yeah, please.
Do we always cut horizontally from like the point?
Cut horizontally from the point. So do you mean like the direction of this box, or?
So at point A, if I make a cut, it's always going to be horizontal. Like, there won't be like vertical cuts.
Well, so are you talking about this box, or are you just talking about this line right here?
That entire line.
Oh yeah, so this line is just means the neutral axis. It's not really a section cut at all. This is just recognizing like this, the vertical and horizontal axis through the center of the shape. We're not really making a section cut. I mean, this box right here, this is a differential element that is kind of cut out of the shape, but don't think of this as a cut. I'm just kind of using these as guides to show this is the horizontal axis, this is the vertical axis. That's really all that I'm showing. Yeah.
When we calculate Q, we make a cut, right?
Yeah, you can think of it as like a line perpendicular to V. Yeah, so don't think of it as horizontal, because I could theoretically give you a problem with a shear force like that, and you wouldn't draw a horizontal line, you would draw a vertical line. So the touchstone is that it has to be perpendicular to V when we're delineating what's the limit of A prime. Yeah, good question. Right, so back to here, what direction is the shear stress going to be at point A due to this torsional moment? Yeah, downwards here, because it is going in the same direction as the torque. So think of it this way. If I was anchored at the centroid, the center of the shaft, what direction would I push on this block to create the same rotation as the torque? And in this case, if I'm anchored right here, I have to push down at A to get that counterclockwise. And so this is going to be tau at A. What about point B? The top of the cross section. Am I going to have zero stress up there just like I had zero stress up here? No. Yeah, what direction is it going to go at B? Yeah, to the left. Being consistent with the torque, this is going to be the direction of each of those shear stresses in the same direction as T. And it's the same kind of idea. I'm actually going to do an intermediate point right here. I'll call it point E. This one I drew off to the left a little bit. I just want to clean this up just to avoid some other confusion. Here, oops, it would be going downwards as well. We're just going to have some intermediate point E that's on the vertical axis, but so for this point E, what direction is my shear stress going to be going? Also going to be going left, but what's different about E and B? Yeah, the magnitude. Why is the magnitude at E less than the magnitude at B? Yeah, rho's different, right? And so I will have some smaller shear stress, and again, there's like a linear relationship with distance and the magnitude of the shear stress. Okay, so now we're starting to visualize, how these shear stresses are acting on these differential elements aligned with the cross-sectional face. And so the question is, if I'm adding these together, how do I deal with that? So here at A, it's relatively easy, right? I have some shear stress here due to the shear force. I have some shear stress here due to the torque. And what's easy about this is that they're both going in the same direction. So let's just go ahead and draw out what this is going to look like, because I'll get my cross section here. and at point A, I'm going to have some shear stress due to the shear force, and I'm going to get some shear stress due to the torsional moment. So this is going to be tau due to the shear force plus tau due to the torsional moment at A. What's going to happen at B? Yeah, I mean, the net is going to be 0 from the shear force and then some horizontal from the torque, and that's all that I get. But it is going in a different direction, which is fine. All right, and then we'll see what happens at, no pun intended, point C. What's going to happen there? Yeah, they counteract. So here, the shear stress at point C due to the shear force is going down. Here, the shear stress at point C due to the torsional moment is going up. And so I'm going to get some shear stress going downwards, TV, and then some shear stress going upwards, tau sub T. And they're going to counteract each other, and you would just need to figure out, here, the signs are not really what I care about. I want you to show me what is the net direction. Is it net going up? Is it net going down? You know, draw me a diagram like this, and then give me the magnitude. That's what I really care about. And then down at the bottom, we can see that we would only get just the shear stress due to the torque. What about point E? Point E is the trickier one, right? Point E, we have some shear stress going downwards due to the shear force, and we have some shear stress going to the left due to the torque. How do I deal with that? We could do a vector sum and give the total magnitude. That would be great. Or you can just say, look, this much to the left, this much going downwards, and that would be fine as well too. But you cannot add them together algebraically. You'd have to do vector addition, doing Pythagorean theorem, a squared plus b squared square root. That would give you the magnitude of the resultant. But you can't just say, oh, the shear stress due to the torque is 5 ksi, and the shear stress due to the shear force is 10 ksi, so the total is 15. That's not the case because they are acting orthogonal. So that's a tricky one, a conceptual kind of hiccup, but I think that visualizing what direction the shear stresses are going on the face is really important, and figuring out when can I add them together, when do they counteract each other, when is only one of them acting at a time. That's an important kind of conceptual thing to be able to understand. So questions about this, how we're adding them together? Yeah, Dylan.
Not really about.
Sure, that's fine.
So are beams or other structures ever designed to have torque or shear in the opposite direction that an earthquake will cause?
Well, so the tricky thing about earthquakes is that they're cyclical. And so it's almost impossible to get different behavior in one direction versus the other. And so when we do like structural analysis for seismic events, we almost always get like, what is the plus or minus value of stress or of moment or of axial force due to the earthquake? And we have to basically say, okay, well, here's our dead load, and then we add 10 kips for seismic, or we subtract 10 kips for seismic. Same thing with shear, same thing with torsion. It's very uncommon to design things to have kind of a non-symmetric response to an earthquake. I haven't worked on anything that does. I could imagine maybe there would be some structures where you might do that, but almost all the time we just basically say, all right, we're going to add the seismic effects or subtract them. That's almost always how we deal with them. Does that answer your question? Okay, that's a good question too. Okay, so then again, conceptually, I had a surveying instructor at OSU that's still teaching. He taught like everyone I worked with, like 70-year-old people who are retiring from engineering. He taught all of them as well too, and he's famous for his little sayings. They're called Schultz's Axioms. And he said, draw a sketch is like, he has this thick like Long Island accent. He said, whenever you don't know, just draw a sketch. And so if you are having a hard time conceptualizing this, you just have numbers on your sheet, draw a sketch, right? Just draw your cross section and then split it up and say, all right, what is the torque doing? What direction are the stresses due to the torque? What direction are the stresses due to the shear force? And then add them up. So often we try to take on too much at once. Same thing with biaxial bending. You can always just break it up into my, deal with that alone, mz, deal with that alone, and then you could even draw a sketch and then try to figure out how they add together. Yeah, Max?
Is the distribution of stress due to the bending moment in that diagram, is that implying it's linear, or would it end up being like second order?
Which one are you talking about? Are you talking about down here? Yeah, so this would be just a torsional moment. And so this has a linear relationship because rho is the only property that matters, and rho increases linearly as we go out to the further distance from the centroid. And so this is a linear distribution. Does that answer? Okay, great. Okay, so let's go back. Let's take a step back. So this is big picture what we're going to be talking about today. I want to get through the rest of the example talking about shear stress because Q inevitably is going to throw everybody for a loop at some point. So I want to go back and just make sure that we really understand what we're talking about when we're calculating Q. Q being the first moment of area on either side of the area represented by either side of the point of interest. And so let's go back to that example out of lecture 9. And let's just refresh our memory. We'll get through most of this. We'll take a break, and then we'll transition over to combined loading. So we have a singly symmetric cross section. It's a unbalanced I-beam where the top flange is wider than the bottom flange. And this is a common design, practice to have it unbalanced. And that's because we might have bridges or buildings that mostly see a positive moment, meaning that most of the compression is up at the top. We don't get a lot of compression down below. And so we kind of, based off the stress profile, we can kind of tailor our cross section to meet that stress profile. So this is pretty common. It just makes it a little bit more difficult for us to calculate Q and to calculate I. And so we went through the process of calculating I. It was basically looking at 3 different shapes. The top flange, the web, and the bottom flange is 3 individual rectangles. And then we said, well, what is I naught for each of those? What is the moment of inertia of the top flange about its own centroid, the web about its own centroid, the bottom flange about its own centroid? And then we had to add on AD squared. AD squared, we call this the parallel axis term. And what do I mean by D here? What is D? Awesome. So Max says D is the distance from the overall centroid of the cross section. So you've already calculated that, like the y bar value. D is the distance from that location. We also call it the neutral axis for our purposes in this class, to the centroid of each of the individual areas. So here from the neutral axis up to the centroid of the top flange, that is D for shape 1. And we do that for each of the shapes. We square it, we multiply times the area of each of the shapes, and that's how we get the total moment of inertia. We couldn't do any tricks with this shape. We couldn't say, well, I can break it up into 2 shapes that have the same centroid, and so I don't have any AD squared term. This is one where we really have to look at it and have a non-zero value for all 6 of the terms that we get here. Because we have 3 different shapes, each of them get 2 terms each. All right, so that's moment of inertia, and again, we have some videos online that can help you out with that as well too. Shear is given to us in this problem as well, and we talked about I. So the 2 things that we need to talk about are Q and T. So Q has a formula that we talked about down below. Q is equal to y bar prime times a prime. Y bar prime being the distance from the neutral axis here to the centroid of the a prime area. Now a prime being the area on either side of the point of interest. So the way that we do that, and Musa was mentioning this before, is here my point of interest is point A, meaning I'm going to draw a line perpendicular to perpendicular to V. I don't have V shown here quite yet. We had it up above. V is going downwards like that. So I make sure to draw a line perpendicular to V, so that's this way, horizontal in this case, that passes through A, and I can choose everything above that line or everything below that line for A prime. Now in this case, if this is my choice, everything above or everything below, it's like which side of the section cut do you take? It won't change your final answer, but it might make your life a little bit easier. So if you want fewer calculations, which side do you want to take for A prime? The side above or the side below? Above, because I only have one rectangle, and this is another common conceptual issue that I see. Some students, when they say, well, take everything below, they say, well, you only have this rectangle right here to deal with. What's wrong about that? They say all that I have to deal with if I choose everything below is just this here. Yeah, it's everything below, even stuff past the neutral axis. It's this inverted T shape. It's the entire rest of the shape below that point of interest. And so a lot of students cut it short, and that's not the right way to do it. You need to consider everything above or everything below. It's a similar conceptual issue with section cuts. A lot of times students will take a section cut and then only keep some of what's on one side of that section cut, whereas you need to keep everything, including reactions, forces, geometry, stuff like that. Okay, so with that in mind, if I keep everything up above, I need to calculate the area A prime for rectangles. That's super simple. If we were dealing with a circle, again, I would either give you a formula for like how to calculate that area above a specific point. That's not a perfect semicircle, but is something between a semicircle and 0. But we're mostly dealing with triangles, rectangles, stuff like that. Area is pretty easy. And then the centroid of that area for simple shapes is also relatively easy. For rectangles, you know it's half the height. For triangles, it's 1/3 of the height from the wide portion of it. You can look that up in the table in your formula packet as well too. But either way, y bar prime is to the centroid of the area. Inevitably, I will see people say, well, y is just the distance to the point of interest. And that is exactly correct for bending stresses, right? For bending stresses, we do m times y, which is the distance from the neutral axis to the point of interest, but we're not using y here. There are like 3 different y's or 4 different y's that we deal with in this class, but the y that we care about here is the y bar prime, which is relative to the centroid of A prime. So I'm just going to put like an x through this. That y is relevant, but not for this analysis. Just keep that in mind. Okay, so this is simply just called the first moment of area. The first moment of area being the distance from our axis of interest to the centroid of an area times the area itself. You might know this, but the moment of inertia that we use in this class is called the area moment of inertia, is also known as the second moment of area. There's a lot of different terms for the same thing. When you get into dynamics, you're going to be using mass moments of inertia, things like that. This is different. This is the second moment of area that we care about for moment of inertia, what we call moment of inertia. And then for this shear stress analysis, we care about the first moment of area, which is just basically a moment arm times an area. Okay, so here it's just simply plug and chug once we've got y bar prime defined, once we have the area defined. And then the thickness, or T, I always call it thickness, but really think of it as the width perpendicular to V. At point A, do I use 200 or do I use 25? There's a hint in the problem statement that tells us which one to use, and we'll talk about that, then we'll also talk about what if it wasn't specific. So what about the problem statement for sub-requirement A tells us that we need to use the 25 millimeter width? Web, right? And we talked about this as well. The vertical component parallel to the shear force is called the web. And even if we had a box section like this, it's the same thing. If V was going down this way, the vertical components parallel to V, both of these collectively would be called the web, or the webs. So here it says the shear stress at point A in the web. The web is the narrow vertical component, and that means it's the narrow component with the 25 millimeter width. What if it just said, give me the shear stress at point A and omitted the in-web component of that request? What would you do? You would just give the answer for both. Because at that point, it jumps immediately from some small value to a larger value as we go from the top down. As we go from the top down, we start out at 0, it increases, and there's kind of a parabolic shape to that increase. As soon as we get to A and then jump across that interface from flange to web, T drops down quite a bit. It goes from 200 to 25, right? So we're talking about like a factor of 12, it's decreasing, and so the stress is increasing immediately by a factor of 12 there. And so I think that we have plotted out for this shape what the shear stress distribution looks like. Actually, maybe that was just in the lecture itself. This is the kind of shear stress distribution that we'll get. 0 at the top because Q equals 0, 0 at the bottom because Q equals 0. The maximum value will occur at the neutral axis because here I have Q max and I have T min at the same point. But at the interface between the flange and the web, we have a discontinuity where it jumps up a factor of whatever the ratio of this flange width to the web width is. And so if it's not clear, if it just says at this point right here, and it could be in the flange, it could be in the web, just give both values just to be sure. But keep in mind that it is transitioning immediately at that point. Okay, so back to the example. The only other thing that I want to talk about with respect to this example is the maximum shear stress. The process for the shear stress at point B is exactly the same as it was for point A. We draw a line that is perpendicular to V, and then we choose everything above or everything below, that line for A prime. For point B, do you want to keep everything below for A prime or everything above for A prime? Probably below. I mean, again, it won't change your final answer, but I think it makes more sense to use this for your A prime of point B area. But you'll get the exact same answer if you choose the T shape up above. Other than that, the same exact procedure as for point A. Now for point subpart C, it says give me the maximum shear stress. And how, again, just remind me, how do I know for sure the maximum shear stress is going to occur at the neutral axis? What's the max of the neutral axis? Q. That does not necessarily mean that the shear stress is going to be a maximum, right? What else needs to be coincident with Q max to guarantee that tau is going to be a max? Yeah, T has to be a minimum. So if at your neutral axis T is a minimum, you're guaranteed to have your largest shear stress there. So, and we do, because here we found out that the distance of the neutral axis is like around 100 millimeters or 100 and something millimeters. Either way, it's in the web, and everywhere in the web I have T min, so I know that at the neutral axis is where we care about for the maximum shear stress. And all that I want to talk about for this is what does Q look like for that calculation. So here we'll call it tau max, and we know it's going to be at the neutral axis because we have Q max and T min at the same time. Okay, so let's get to that subpart right there. So I'm just going to choose everything above the neutral axis for this. We know the distance from the bottom of the shape to the neutral axis, and then so I can split it here, then keep everything above the T shape up here, or keep everything below the T shape down below. It doesn't really make a difference either way. And so I'm going to make a new diagram that has the top flange and it has the portion of the web up until the neutral axis, because that's where my point of interest is. Here's my point of interest. And so I've drawn basically a line through the point of interest, which is coincident with the neutral axis, and now everything above is what I'm going to use for Q. So Q at the neutral axis is the same equation as Q for anywhere else. It is y bar prime times A prime. But here, I'm really looking at like two different discrete shapes. We've got a top flange and we've got a portion of the web. You could find the total area for both of these shapes combined, and you could find the centroid of both of them combined, because as it stands right now, they each have their own local centroid, but there's also like a overall centroid for these as well too. So if this is y bar prime, we'll just call it like total, we could find the actual centroid of both these shapes combined. I'll call it y bar prime total, and then multiply it times the total area. So I could just say this is y bar prime total times a prime total. But that's a pain. I don't want to have to like figure out the centroid of these if I don't have to. And fortunately, you don't have to, because all you would have to do if this is shape 1, if this is shape 2, all that you would have to do is y bar prime for shape 1 times a prime of shape 1 plus y bar prime of shape 2 times a prime of shape 2. You don't need to go through the intermediate step of calculating the overall centroid, because this equation here, where it's just the distance of the centroid for each of them, this is y bar prime 1, and this here is y bar prime 2. You can just do them individually, add them together, there's no difference. So just trying to save you some work. Either way works, but here you have some intermediate calculations to calculate y bar prime total and a prime total, which is kind of a pain. Okay, so any questions about this? We're just making the shape for a prime a little bit more complex, but we can again do the same thing of dividing and kind of conquering that as well too. And we've already talked about subpart D, which is what is the shape of the shear stress diagram. We talked about that in the lecture slides itself, and that is, it's going to look exactly like this. So one question I do have, and this is more conceptual, this isn't something that I'm necessarily going to put on an exam, but how could I get, like, what is the relationship between V and like the area of this shear stress diagram? Or in other words, when we were looking at like bending stresses and we knew what the stress distribution was for the top flange and the bottom flange, we could calculate how much force each of those individual elements were exhibiting just by multiplying like the stress times the area, like the average stress times the area. It's the same thing here. If you think of this as like a 3D stress distribution, like if I were to plot out, if I were to take like these distances here and plot them out on top of this shape, you know, coming out of the page with, like this is the side view, this is the front view. If I combine these into like a three-dimensional kind of representation of the stresses, that volume altogether has a, like the length in and out of the page would be in terms of like KSI, and then the projection on the cross section would be like inches squared. And if you took the volume, that's like KSI times inches squared would be kips, and that would be equal to this shear stress exactly. And so think of it that way, as if we were to plot out the stress profile onto the face of the cross section, make a 3D element out of it, the depth in and out of the page is like stress. On the page itself, the cross section, we're looking at area. Multiply those together, get the volume. That is the actual resultant force, whether it's a shear force or a moment, anything else like that. That's a good way to think about it, kind of maybe in a more spatial way. All right, any wrap-up questions about how we go about the process of going through a shear stress calc? Yeah, Max.
I just wanted to clarify, when calculating Q at the neutral axis, you're doing the summation of y bar prime times a prime for the total, or a prime for each?
So a prime 1 would be the area just of shape 1, and a prime 2 would be the area just of shape 2. A prime total, this right here, this is simply equal to a prime 1 plus a prime 2. Yep, but if you're breaking it up with separate y-bar primes, it's just times the area of shape 1, area of shape 2. Okay, so let's take a break. When we come back, we're going to talk about what we started talking about at the beginning of lecture, which is how do we combine all of this together and get like a big picture view of what the stress is at a single element due to multiple loading at the same time. So let's take about, 7 or 8 minutes, come back around 15 after, and we'll get into an example of that. Okay, so a couple good questions came up over the break that I want to chat about just really quick. And so when I was mentioning like the volume of a shape that's created by looking at the cross section, and the depth would then be the stress profile itself, I think it's a lot easier to conceptualize that with a rectangular cross section like this. So imagine this is our shear stress volume on this rectangular cross section. It is parabolic in nature, and if I were to plot that above the cross-sectional area itself, the volume of this shape has units of KSI times area, which would give us, or like times inches squared, which would be kips or force. This volume has to be exactly equal to this shear force right here. It's the same exact thing for the stress volume for normal stress due to a bending moment or normal stress due to a normal force. The volume of this area defined by the cross section, and then the depth being the stress, the volume is going to be equal to whatever is causing those stresses, whether it's a shear force, bending moment, normal force, torque, anything else like that. So I think it's an interesting way to visualize it. I think it might help some people. The other question that came up over the break that I thought was good is, well, what if I have a box section like this? I'm still trying to calculate the shear stress at my point of interest, but if tau equals VQ over IT, what could maybe throw you for a loop if we're looking at this point of interest? Right, I'm still going to do the same thing for A prime. I'll draw a line perpendicular to V. I can choose all the area above or below. So I mean, even though A prime now is like either one positive shape and one negative shape, or you could look at it as like 3 individual positive shapes, calculating Q is not really going to maybe throw us for a loop. But T, yeah. So is T going to be this width or both of them combined? It's going to be both combined. It is the width of the cross section at the point of interest, and the width is the combined width all the way. Now, one of the sections that we're skipping has to do with what's called shear flow, which would be, well, what if I was putting nails in to attach, or like welding like this point here and this point here? Oftentimes what we would do is we would kind of like cut this area in half. But let's just talk about that. If I were to simply like cut this area in half and just say, well, half of this area is being held on by this interface down here, I'll just call it like, let's just call it like 2 inches. And then the other half of the area is being held on by this other interface on the right-hand side that's also 2 inches wide. If I choose T to be 2 inches, it all works out in the wash because my A prime area associated with this width is half as much. So I can either do the total area with a width connected of 4 inches, or I could do half of the area with a width connected of 2 inches. And because one is in the numerator, the other is in the denominator, the ratio is the same. But if you're doing the total area, it would be the total width, even if there's gaps in it. Whatever width crosses that line that you draw perpendicular to V, all of that combined is T. All right, any follow-up questions about that? Okay, so let's talk about just really quickly the things that we're skipping over that I'm going to provide some extra credit for. So Beams 4 talks about shear flow, and I just alluded to it just a second ago. I just want to give you a 5-minute kind of synopsis of it. So when we build a cross section, it is very common to have it made up of like different materials or different parts that are attached at some point. So if I had like, if you're familiar with like residential framing and stuff like that, a lot of the floor joists that we have nowadays have like a fir top piece to deal with moment, an oriented strand board, like kind of a crappy plywood web, and then at the bottom we'll have like a higher quality fir like bottom flange. And then these are attached either by some combination of glue or nailing, maybe one or the other. But the point is they're attached to each other. Now, if this was a beam that I was trying to design to carry some sort of, say, distributed load, point load, whatever else, it's going to be subjected to a shear force and a bending moment. When we usually think about the shear stress on this, we're often conceptualizing like just the shear stress on this cross-sectional face, like the shear stress going up or down. But due to the complementary property of shear, what other direction is the shear stress going? Yeah, in and out of the page. And what that does is it creates like a force in and out of the page that's differential on this element and then the element that is connected to. So as I apply a shear force to this, that web is going to want to move longitudinally versus that top flange. And you can see this just in practice really easily by looking at, where to go? We've got a nice example of this. And actually, it might even be in lecture 9. Let me just jump back, because I think it's valuable to see, because as soon as you see it, you're going to say, oh yeah, I get that intuitively, that is going to make sense. If we have 3 boards that are stacked on top of each other, think of them as frictionless boards. If they start out exactly the same length, perfectly stacked on top of each other, they're just going to look like one big rectangle. And all of the ends will line up and everything's perfectly square. As soon as I put a load on top of them, what happens at the ends? They like slide relative to each other. That is caused by a longitudinal shear stress. And it's all about like each of these are acting as independent beams where the top gets shorter, the bottom gets longer, and so that difference right there, if these are free to slide relative to each other, that's a longitudinal shear stress causing that. Now, if we don't want that to happen, it's for good reason. We get a lot better structural performance if instead of being 3 individual separate beams, these all act together as one cohesive cross-section. Because here, if I were to calculate the moment of inertia of this, it would just be the moment of inertia of this, plus a moment of inertia of this, plus a moment of inertia of that. No AD squared term at all. Just be 3 times 1/12 base times height cubed. If we attach them, if we bond them, then all of the ends still line up. If we were to glue all of these together, all the ends line up, and now they act as one complete cross-section, and we get beam action where the moment of inertia now is not just 3 times the moment of inertia of one of them, it's like a lot bigger than that. It has that AD squared term value now. Now, the difference is that we have glue between here now, but the question you're going to have would be, well, how strong does that glue need to be? Or if we're nailing this at multiple different locations, you know, what is the demand on that nail, or how many nails do I need to put in there? And that's fundamentally still a shear stress investigation, but we call it shear flow, and there are some specific like applications of it, whether we're talking about glue or discrete fasteners like nails or staples or welds and things like that. But the reason we're going to skip over this is that, number one, you know, I never learned this in my strength and materials class. I learned it in my design classes later on, which is generally speaking when it's going to come to the forefront. And 2, because the equation is so similar to what we've already done for shear stress itself. Shear flow, for whatever reason, Hibbler calls it lowercase q. So now we deal with Q and Q, which is kind of a pain, but we can deal with it. lowercase q is called shear flow. It's equal to V times Q over I. What's missing? T. So what are my units going to be here? If I'm missing a linear dimension in the denominator, instead of being like kips per square inch, what am I going to get? Kips per inch. Which means this will give me the demand in terms of force per foot in and out of the page, or force per meter in and out of the page that I have to resist. And so that's the difference about shear flow is we're clearly talking about the forces in and out of the page longitudinal to the beam. Now Q is just very, very slightly different because when we talk about a cross section, we're talking about, we're focusing on like how many points of attachment there are. And so if I had a cross section that looked like this, where it's like 5 different rectangles, I've added on some little stubs here to maybe increase the moment of inertia. We're focusing, like I'm just putting nails in between all of these here. If I want to know what the shear flow is along this interface right here, my A prime area, Q is still calculated the same, Y bar prime times A prime, but A prime now is the area that is attached to the rest of the cross section. Meaning I can either choose everything on either side of this joint. Now, when I say on either side of that joint, I mean everything attached to it on either side of the joint, which is a little bit different. If I choose everything above, it's not only going to be just this top flange, it's also going to include these little stubs as well too. It's everything on either side. Whereas if we're doing the shear stress at this point, I would do a horizontal line. With shear flow, all that I'm doing is I'm saying everything on one side or the other of this, and you just kind of follow how everything's connected to each other. The other trick about this is what if we had like 2 different points of attachment, and that would be an example of like the top here. If I was interested in figuring out, well, what is the demand on like this interface right here, the nailing between this stub and the rest of the top flange, I could either choose like this area right there for A prime, or I could choose this area over here for A prime, but then divide it by 2 different points of attachment. So this is a little bit of extra bookkeeping, but fundamentally Q is calculated essentially the same way. A prime is just slightly different. And then you have to keep track of, well, how many points are attaching. That helps you define A prime. So it's really just a slight extension of VQ over IT, which is why you have the tools to be able to do this. Just a couple tweaks to the methodology, and then you'd be completely well versed in it. So we're going to skip over this, but it does help when it comes to attaching different pieces and figuring out what is that demand. Yeah, Dylan.
So if it was only attached at that center piece and those little edge squares were already there, they didn't need nails, would you still include them?
You would still include them. Yeah, good question. So Dylan's saying, well, what if these weren't, what if this is all monolithic top flange, there wasn't any other pieces attached? You would still include the entire top flange for the shear flow here at that web to flange connection. Yeah, Max.
Just clarify, would be we're using the complementary V in the X direction in this case?
No, this would be, yeah, great question. Really good question. V here is still the transverse, like the vertical shear force. This is simply causing a shear stress in that longitudinal direction as well too. And that is what is driving that desire of the flange and the web to move this way. But the actual demand V, you get from your shear and moment diagram, the same exact V you would use for shear stress. Great question. Now, there are extensions of this shear flow into topics that we wouldn't even get to even if we had time in the class, things like shear center. So all of our cross sections that we deal with so far for shear have to be symmetric about the axis that V is acting in, and we won't deal with any that aren't, but I do just want to give you a heads up. When we do have a cross section that's not symmetric, let's say like a channel, and I have some shear force applied to it like this, now the section is not symmetric about the application of the shear force, which we can't deal with, But what do you think is the issue if I have this shear force applied here and I apply it at like the geometric center of this shape? What ends up happening is if it's not going through what's called the shear center, it causes a torque on this cross section as well too. And being able to calculate, well, how far are we away from the shear center is an extension of kind of this shear flow concept as well too, where we plot out how the shear flow varies, not even just the connections, but everywhere in the cross section. We plot it out, and then we find the centroid of that shear flow area, and that tells us where the actual shear center itself is, which is not the geometric center, just to be clear. So that's another more advanced topic. They kind of go hand in hand, and we always have to cut short, usually between shear flow and shear center, but this time we're just cutting short of shear flow. But I will give you a lecture online and give you some extra credit if you want to investigate that a little bit further. Yeah, Max?
So just to clarify, using this method, it's going to define the shear flow in the x direction?
In the longitudinal direction, exactly right. The forces that we care about here are going in and out of the page, trying to load this nail right here. It's trying to make that break this way. It doesn't care about how much does this little block weigh and is it going to fall off. It's not loading the nail in axial like tension. It's loading it this way like the nail is going to break like side to side. Okay, so that's one thing. Like I said, I'll provide some supplemental material, opportunity for some extra credit, but we're not going to cover it for the exams or the recommended problems. And I've already updated the recommended problems for that. The other thing that we're going to skip over, which again is a very quick kind of calculation, is the thin-walled pressure vessels. And all that I want to do is just give you a quick heads up about what this looks like. We use a lot of pressure vessels, liquid storage, gas storage, things like that. And we need to figure out, well, like how thick does that metal or plastic or whatever else need to be? And not surprisingly, if I have a differential pressure of the inside of the vessel versus the outside of the vessel, I'm going to get some stress in whatever that wall is. And all that we do is we split it up into two different shapes. We have cylindrical vessels, and then we have spherical vessels, and that's the only two that we get to deal with. And we're limited to just thin-walled pressure vessels, meaning the inner radius divided by the thickness has to be greater than or equal to 10. There are thick-walled pressure vessels. We don't have the equations to deal with that in our textbook, but they do exist. This is a really short section in your book, and basically there's only two different stresses that we care about. One is called a hoop stress, which is going transverse to the longitudinal axis of the member. It's basically going in the circumferential direction around the cylinder. And the other one is called longitudinal, that is going parallel to the longitudinal axis of the vessel. In this case, sigma 1, the hoop stress, is always twice the value of the longitudinal stress, which is why you often see failures of, let me get past the derivation, which is why you often see failures of cylindrical pressure vessels like this. So this would be like a rifle stock or something, not stock, but barrel, plugged up at one end, explodes, and then it breaks in the longitudinal direction because that's a failure in the actual hoop direction. It's like it failed in tension in that circumferential direction. Same thing here with like a pipeline rupture or something like that. Spherical vessels, it's the same idea. The only difference is that instead of getting a hoop stress and a longitudinal stress, the only stress that we get is the same in every direction for a sphere. We call it sigma 2. And the equations are relatively straightforward to apply. It's the pressure times the radius, either divided by twice the thickness or 1 times the thickness. They're exactly the same whether it's hoop or cylindrical, or sorry, spherical. It's just we divide by 2t or we divide by t. Just internal pressure, internal radius, and thickness are all the things that you need. So it's really quick to apply. It doesn't really deserve a whole lecture unto itself, and we're going to skip over that as well too. Just like the other material, I'll provide a quick small homework assignment for some extra credit for this as well too. But your book doesn't devote a lot of time. We're not going to spend a lot of time on it either. Actually, we're gonna spend like no time on it other than this, just to kind of introduce it. But where this takes us is the topic that we were talking about at the beginning of class, which is combined loading, which is we know how to deal with the normal force and what kind of stresses it produces, torsional moment, chapter 5, and the stresses it produces, bending moment, chapter 6, and the stresses that it produces, and now shear forces and the stresses that it produces from chapter 7. What happens when we have multiple loadings on the cross-section acting at the same time? And that's what chapter 8.2 in your book is all about. And that's a really good review of all the loadings that we've dealt with before, kind of all together. And so we have a lot of structures that have multiple internal resultants acting at the same time. We don't live in a vacuum where we only get N or T or M or V acting at the same time. And so what about this bridge like column right here? This bridge column, right, most bridges are near and dear to my heart. That bridge column, is it subject to N, T, M, or V? Or like some combination? What do you think? Yeah, what is going to cause a normal force on a cross-section of that column? Yeah, wait. Dead load, live load, vertical forces transferred to the, like from the bridge deck right there are going to make their way into that column, and it's going to be a normal force because it's perpendicular to a cross-section through it. Great. N is pretty easy. M. Why am I going to get M? Yeah, I have some eccentricity. If I have a force going down like that, there's some eccentricity there. That's going to cause a moment, a bending moment in that column as well too. Absolutely. I could have an earthquake, right, that applies, let's say like a horizontal force, and that's going to cause a moment as well too. Am I going to get any torsion possibly on that? Yeah, if the bridge, like superstructure itself, if this is expanding or contracting, thermal effects, stuff like that, I could get a force parallel to the deck, a force like this, that causes some torsional moment because of the eccentricity to the longitudinal axis, the vertical axis of the column. So I could get a torque there as well too. Right, this force here is also going to cause a shear force on the column as well. Wind loading, the load of a vehicle braking, the wind load on a vehicle, these are all loads that we have to care about. Impact, stuff like that. This, we would have to look at all of these possible internal resultants from any multitude of different load cases. And we have a lot of them to deal with. So we don't design in a vacuum. We have to consider all of the effects, and most of the time, it is going to be, the majority of these possible internal resultants acting concurrently. And that's the kicker, concurrently, meaning we've got to add up the results of all of them. Now, I even had one other one. Now, I realize that we're not covering thin-walled pressure vessels, but this is a steel jacketed column, and some students last year, the year before, said, well, if this was in place before they poured all the concrete in, we could even maybe consider this a thin-walled pressure vessel if that concrete in its liquid form was acting like with a hydrostatic pressure. We could even say this would be like a thin-walled pressure vessel too. I think that's probably how they built it, so that's a valid loading as well too. So even though we're not going to cover it, this is another loading that we would have to consider as well. So Max is saying, would the normal force cause strain in the concrete? Yeah, once it's cured, absolutely. You would get a composite action then as well too. So you can see really quickly, for a relatively simple structure, our loading gets to be really complex. So it's all about bookkeeping. It's all about figuring out, there's even temporal effects as well too. So if we have pressure when before the concrete is cured, then we have a different cross-section to deal with for some of the loads, and we add stiffness. Even there's time-dependent properties we have to deal with as well too, but it's all about what are the loads and then keeping track of when they're applied, what kind of a cross-section they're applied to, and it quickly balloons out of hand and just becomes, that's why designing something like this can take, months if not years. Okay, so with that in mind, the fundamental procedure for dealing with this, it is the same as what we've been doing so far. We're just adding everything together. Assuming that everything's linear elastic, we can just superimpose the results at the end. So we need to figure out our internal loadings. How do I figure out N, T, M, and V? Section cut, free body diagram, equilibrium. Always is going to work. Now, if you have some graphical method shortcuts that you're comfortable with using, that's one way to get to it as well. But equilibrium, free body diagrams will always get you to this point, or it might be given to you. But this is step number one. What are the internal resultants? Step two, what are the stress components? And that's each of these equations down here. So in the longitudinal direction, this is more important when we dealt with thin-walled pressure vessels. I'm just going to simplify this and say sigma and tau. All that I've done is I've crossed out the pressure vessel components. I'm going to still let you see them, but we're not going to deal with them on a computational level. What are all of the components for sigma? That could be the normal force, N over A, mz times y over iz, my times z over iy, and then add all of those together at a specific point. Same thing, vq over it, t rho over j. And just keep in mind that here we have the plus or minus symbol. For sigma, if I have my coordinate system set up correctly, if I follow my sign conventions, the signs will always work out here, where negative means compression, positive means tension. The signs and the coordinate systems are set up to make this just basically an easy way to figure out is it compression or tension. Just follow the sign convention, it'll work out. For the shear stress, just like we saw with the figures at the beginning of lecture, it's a little bit trickier than that, right? Sometimes you have shear vectors going this way combined with shear vectors going this way. And you've got to figure out, maybe you go with a vector sum, if not parallel. I say or report each direction separately. Each direction of tau separately. And that's really what this note is saying here. If you have orthogonal directions, draw a sketch, right? Show me what the stresses look like if they're not going in the same direction. And that's it for combined loadings. It is do what you did in chapter 4, 5, 6, and 7, and then add together the results. It's just a bookkeeping and kind of maybe conceptual kind of graphic exercise, making sure that you're adding them together where they should be added together, you're subtracting them where they should be subtracted, and then especially with shear stress, making sure you're identifying what direction the stresses are actually going. All right, so it's a good review, and it'll help you with what you're doing on the second exam as well too. And so let's just talk about, out of your book, it's got some really good examples with many different types of loading that I think is going to help you out. So examples 8.2 through 8.7 do a really good job of walking through different examples where we might get multiple different loadings on a cross section and then how to deal with them each individually. So for example, let's just talk conceptually about this one. So here we've got a single point load applied to this, and then it's asking for stresses on a cross section that passes through B and C. Is this an axial load, the 150 pounds? Yeah, so axial load is defined by two things. So what do you think? What does an axial load need to be? Yeah, it needs to be parallel to the longitudinal axis. So far, so good. 150 is parallel to the longitudinal axis. And it needs to be what? Yeah, at the centroid of the cross section itself. So coincident to the longitudinal axis. Here it's not. It's offset, just like Max said, by 5 inches. We call this an eccentricity. This has an eccentricity from the centroid of 5 inches. Meaning it's going to cause what if I made a section cut through here? A moment. And so let's just say we're making a section cut through here. I have a possible internal normal force. I have a possible internal moment as well too. And if I were to just run equilibrium, I'm just going to make up a coordinate system here really quickly. Let's just call this X. Let's just call this, actually we'll do Y the other way. let's call this y, and it doesn't really matter. This is all arbitrary anyway. We'll call counterclockwise positive. All right, sorry about that. We're back on the blue light. So if I were to sum the forces in the x direction equal to 0, we say that positive x is down. It doesn't make any difference. I get positive 150 pounds going down. That's the applied force right there, plus n. So n equals negative 150 pounds. It means it's in compression on this cross section 150 pounds, which is pretty straightforward. I think that almost everybody can get to that point right there. It's the eccentricity that throws some people for a loop. So when we take the moments about a section cut, we often say that we're taking the moments about like point O. Point O is at the centroid of that cross section. Meaning when I sum the moments about point O, counterclockwise being positive here, M is clearly causing a moment about O. This is a couple moment. I can just say that is causing a positive M moment about O. What about the 150 pounds? Is that causing a moment about O?
Yes, it's negative, right?
Yeah, it's going to be causing a clockwise rotation about O because 150 is pointed down on the right, going clockwise, so it'll be negative 150 pounds times 5 inches. So I get that M equals positive 750 pound inches. So as a result, if I cared about this point C right there, what kind of stresses am I going to get due to the normal force? It's all about sigma equals n over a minus mz times y over iz. N here is negative. The area is just 4 inches times 10 inches, so it'll be the 150 over 40 square inches. Same thing with mz, y over iz. We're going to want to draw a cross section. C is going to be up on the top, and then we need to figure out is m positive or negative, what is the y coordinate of C, and then calculate the moment of inertia of that rectangle. So we'll continue this discussion a little bit more after, next Thursday. But this is also good review even for the exam coming up because it does combine basically everything that we've learned. It adds shear stress as well, which won't be on the exam. But if you want to look ahead a little bit, this combined loading, I think, will help you think about how all of these stresses act together. I know a lot of you have an exam, so I'll let you out of here a little bit early. Exam next Tuesday. I'll post the solutions for the example that I was going to give you today. Other than that, I'll see you next week.